All right, hello everyone, and welcome to 7.9 and 7.10 in the AP Chemistry Equilibrium unit. Today we are talking about Le Chatelier's principle and then how that relates to our reaction quotient. So Le Chatelier's principle states that when a system at equilibrium experiences some sort of external stress, it's going to respond in a way that offsets that stress. So these stressors can include adding or removing a reactant or a product, changing the temperature, changing pressure or volume in a gas system, or diluting a solution. The system shifts its position of equilibrium to partially counteract the change and level out as much as possible. And today we are lumping in 7.10 because all we are doing extra is relating Le Chatelier's principle with Q, our reaction quotient, which was kind of already done in this lesson. So it made a lot of sense to loop it in. So Le Chatelier's principle explains how a system at dynamic equilibrium responds when conditions such as concentration, pressure, or temperature are changed. So the system shifts in a direction that's going to counteract the stress and reestablish equilibrium. This principle allows us to predict how equilibrium systems will behave when disturbed and then connects directly to reaction quotient concepts, which we will use to explain these shifts mathematically. A few important points to remember for this video and for the entirety of Unit 7. Number 1 is that equilibrium constants are constant at a constant temperature. So what that means is the equilibrium constant is only going to change if you change the temperature. If the temperature remains constant, then the equilibrium constant is also constant. The next point is that the position of equilibrium can change when concentration, pressure, or temperature changes. And then finally, if a catalyst is ever added into an equilibrium, it is not going to change our equilibrium constant K. It's also not going to shift equilibrium. It's just going to increase the rate at which we get to equilibrium. All right, so our first stressor is concentration. So when we change concentration, we're going to see a shift in our equilibrium, but just remember the equilibrium constant is going to remain the same because temperature is constant. So first let's talk about increasing concentration. So let's say we have a very basic reaction. So we have 2 red reactants and 2 purple products. So what happens if I were to add in 2 more red reactants? Well, right now, if we're looking at our equilibrium equation, we are at a K of equal to 1. However, when we increase the number of reactants, so now I have 4 instead of 2, I now created a K that is less than 1. So my equilibrium constant is still K equals 1, but right now my Q is K is less than 1. So because Q is less than 1, I want to shift back towards the product side so I can get back to a K of equals 1. And now that I shifted back towards the product side, I again have a K of equal to 1 because I have the same number of reactants to products as I started with. Now let's say we decrease a concentration. So let's say we decrease the concentration of our products. So again, right now I have 4 reactant particles and 4 product particles. So technically my equilibrium constant is equal to 1 because I have the same number of products and reactants. Now if I were to decrease my amount of products by 2, now my equilibrium is going to shift to the right to counteract that change. So at Q right now as we speak, we have again more reactants than products, so our K is less than 1. So we need to shift back to the right in order to get our K back to 1. And then we are back to equilibrium. All right, so let's break that down one more time. So if we were to start at equilibrium where Q is equal to K, we have a ratio of products and reactants that matches the equilibrium constant at that temperature. Now, if you were to increase the concentration of products, you are adding product to the numerator, which is going to increase that Q, or reaction quotient. And because we have a higher number of products, we need to consume those products and head back towards the reactants. So since we are shifting left, we are making more reactants, and then eventually we will get back to equilibrium, where our ratio of products and reactants matches that equilibrium constant. All right, our second equilibrium stressor is going to be pressure, and it's really important that you know that pressure is only going to affect equilibrium if you have gases involved. So only with gases. The other thing that's really important is you have to have a different number of moles of gases on either side of your equation. So if you have something like A, which is a gas, plus B, which is a gas, reacts to form 2AB, which is also a gas, we have 1 plus 1, or 2 moles of gas on the left and 2 moles of gas on the right. So if we were to increase or decrease pressure, we're not going to move in either direction, or we're technically going to move in both directions simultaneously, because there's not one side that has less or more moles. So watch out for that. So if we were to increase pressure, I want you to think in your head about Boyle's law. So if we were to increase pressure, that decreases volume. So if we have the same number of particles now in a smaller space, those particles are now going to collide more frequently, which would do a lot in terms of reaction. So in order to offset that stressor, what we need to do is shift to the side with a lower number of moles. And by shifting to the side with a lower number of moles, now we can reduce those collisions in that vessel. And same going in the opposite direction. If we have a system where we decrease pressure or increase volume, we now have those particles in a larger space. So in order to keep up that collision rate, we need to move to the side of the equilibrium with a lot more moles of gas so that we can keep that number of collisions up. All right, so let's look at what that looks like. So at the left, we have the system at equilibrium. We can see that we have 2 moles of each reactant, and then we have 2 moles of product. Then we are going to put this in a larger container, or expand the container, and we now have those same 6 particles in a larger space. And because they're in a larger space, they're technically going to collide less often. So to keep the equilibrium constant the same, we need to introduce more particles so that we can keep that collision frequency going. And as you can see in the top equation, we have 2 moles on the left of gas and only 1 mole on the right of gas. So by shifting towards the left, we are doubling the amount of particles per every product that is converted into reactants. So temperature is different from concentration and pressure, because when we change concentration or pressure, we're only disturbing the reaction temporarily until that system shifts and returns back to K, or the equilibrium constant. Now temperature, when we increase temperature, we're actually changing the energy of the molecules, and that's going to affect collision energy, activation energy relationships, and the relative speeds of the forward and the reverse reactions. And because those rates change differently, the equilibrium ratio is also going to change, which changes K. So whenever you are looking at Le Chatelier's principle in temperature, you have to know what type of reaction it is, exothermic or endothermic. And that is going to help you decide where it's going to shift. So if we have an exothermic reaction, it's best to think of the heat as a product because we are releasing it. And then for an endothermic reaction, it's best to think of the heat as a reactant because we are absorbing heat into the system. Now, if you think of heat as a reactant or a product, the idea is very similar to concentration. If we are increasing temperature, we're increasing heat, so we want to move away from the heat. So if that's an exothermic reaction, that means we're moving towards the reactant. If that's an endothermic reaction, that means we're moving towards a product. Then the opposite is also true. So if we decrease the temperature, we want to increase the amount of heat. So for an exothermic reaction, we're going to move to the product side. And for an endothermic reaction, we're going to move to the reactant side. So let's look at this example and see what happens when we increase the temperature of an exothermic reaction. So at the top of the image, you can see that the reaction produces heat. So heat is treated like a product. When we add heat to the system, it's like adding more product. So according to Le Chatelier's principle, the system will try to get rid of that extra heat by shifting in the direction that absorbs it. So that is going to be towards the reactants. So since absorbing heat is endothermic, the reaction is going to shift to the left, which is the reverse reaction. Now, as the system shifts to the left, more reactants are going to form, and the amount of heat being produced is going to decrease. And then our last stressor is going to be catalyst. Now, it's really important that you know that when you add a catalyst, we are not shifting equilibrium and we are not changing the equilibrium constant, because all adding a catalyst is going to do is allow it to reach equilibrium quicker or at a lower temperature. So when we add a catalyst, it's going to decrease the activation energy of both the forward and the reverse reactions by the same amount. So because of that, it's not shifting anything, it's just allowing us to reach equilibrium at a faster pace. So let's go through a couple example problems before we close out this lesson. This FRQ says the following particle diagram represents the equilibrium mixture before the temperature is changed. In the empty box, draw an appropriate number of each type of molecule to represent a possible new equilibrium at a lower temperature. So, looking at the equation above, we can see that we have a negative delta H value. And negative delta H is going to tell me that I have an exothermic reaction, which means my heat is a product. So if I am lowering the temperature, I want to move towards the heat. So I am moving in the forward reaction or favoring the exothermic reaction. Now currently in my filled box, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of my product, and I have 2 of each of my reactants. So since I'm moving in the forward direction towards the heat, which is towards the products, I am going to be making more HI. So I only have 2 molecules of each of my reactant, and we don't want to completely eliminate the reactants because that means equilibrium is no longer able to exist. So we're just going to take 1 of each of those. So we're going to get rid of 1 of our H2s and 1 of our I2s, and we're going to be able to make 2 of our HI product. So let's go ahead and draw our reactants first. We have 1 of each left. And then again, we originally had 10 HI molecules, and now we added 2 more, so 12 HI molecules. And just make sure they're sporadic and rotated. And that could be your answer. All right, this next example says another mixture of PCl3, Cl2, and PCl5 is at equilibrium at a different temperature in a different vessel. The system at equilibrium is represented by the following box on the left. Then the volume of the vessel is decreased. The box in the middle represents the system before equilibrium is reestablished at the same temperature. In the box above on the right, draw an appropriate number of each type of molecule to represent a possible new equilibrium. So looking at our equation, you can see that we have all gases, which means if we are decreasing the volume, that means we're increasing pressure. And since we want to keep our same equilibrium constant, we need to decrease the pressure or reduce the number of collisions. And in order to reduce the number of collisions, we need to move to the side with less moles of gas. So on the left, we have 2 moles of gas, and on the right, we have 1 mole of gas. So I know in my new equilibrium, I want to shift towards the right, which means I'm going to produce more PCl5s. So because I need 1 PCl3 and 1 Cl2 to make a PCl5, I'm just going to remove one of each reactant. So 1 Cl2 and 1 PCl5, and that means I'm going to have, we could end up with something like this. So we can see that we took out 2 of our reactant species, so 1 PCl3 and 1 Cl2, and we use those 2 in order to make 1 PCl5, which reduced the number of particles in the vessel, which is going to reduce the number of collisions and therefore reduce the pressure.